Ravel's Introduction and Allegro may seem a far cry from the vibrations of springs and pendulums that you've been experimenting with in this unit. But musical instruments all rely on vibrations of one kind or another to produce musical sounds. And in this program, we'll be looking at a number of musical instruments, particularly the violin, with a view to extending the discussion of vibrations that you've been concerned with in the main text. We'll look at what happens when systems are forced to vibrate, as well as what happens when they vibrate freely. And in particular, we'll be concerned with a phenomenon known as resonance. But first of all, let's have a look at a few musical instruments.
In fact, man's shown great ingenuity for finding a whole variety of different systems to act as the primary vibrating source in musical instruments. For instance, in the string family, such as this cello or the violin, it's the string itself that is the primary vibrating source. And in the piano as well, it's strings that act as the primary vibrating source. But of course, in the wind family of instruments, such as a clarinet, it's a vibrating column of air that's the primary vibrating source. Now, you can think of these as being one-dimensional systems, a one-dimensional column of air or a one-dimensional string. But we can also make musical instruments out of two-dimensional systems. For instance, a two-dimensional membrane forms a very good drum. Or a two-dimensional plate is a beautiful gong. But one thing all these vibrating systems have in common is that when they're displaced away from their equilibrium position, there's a restoring force which opposes that displacement. And it's this restoring force, provided here by the elasticity of the string, which causes it to vibrate. With the air column, the air itself has a sort of spring. So that when I push the piston in, the air forces it back up again. And similarly with the membrane. If I displace the membrane, there's a restoring force, again provided by the elasticity, which causes it to vibrate. Now, all these systems have a natural fundamental vibration frequency. But with musical instruments, we'd really like to be able to play tunes. We'd like to be able to change the frequency. And we can't really do that unless we understand what it is that determines the frequency of a string or a vibrating air column.
Well, what determines the natural frequency of a string like this? There are three important factors. First, there's the tension, and here that's provided by the weights on the end of the string. With 4 kilograms on the end, the natural frequency is about 260 hertz or so. That's around middle C on the piano. But what will happen if another weight is added to increase the tension? The frequency, the pitch of the note, goes up. Increase the tension some more, and the frequency gets higher still. What's happening is, as the tension gets larger, the restoring force on the string gets larger as well, and that means that the string vibrates more rapidly. This dependence of frequency on tension is used to tune the notes on pianos and other stringed instruments. What else affects the natural frequency of a string? Well, I've got a second string here now, and it's got a larger diameter, so it's got more mass, more inertia if you like. It's under the same tension as the original string, but compare the frequencies. The heavier string has the lower pitch, so the increased inertia slows down the vibrations. It reduces the frequency. The third factor that determines the frequency of the string, and probably the most important one, is its length. As the length of the string decreases, the frequency gets higher. And after a bit of practice, it's even possible to play a simple tune on here. Well, I'm obviously not an expert yet. On the piano, a whole range of notes is obtained by using strings with different mass and with different lengths. The lowest frequencies require a combination of high mass and long string, and conversely, the high notes require strings that are light and short.
Length's also an important factor for wind instruments. This is my all-purpose wind instrument, a sort of hose-pipe clarinet. And it's not bad either, is it? Here, it's the length of the vibrating air column that determines the frequency. And I can prove that to you with a little bit of help from Stuart. Well, I think you get the idea that the shorter the column of air, the higher the note. But this is a little inconvenient, to say the least. For one thing, it's irreversible. I can't go back again. With a real clarinet, of course, what happens is that I can shorten the effective length of the pipe by opening holes up the side of the tube. The further up the pipe the hole is open, the shorter the effective length, and therefore the higher the note.
It's the same with the xylophone. The shorter bars have higher frequencies than the longer bars. And we get the same effect with timpani. The small drum has a higher pitch than the larger drum.
Okay, so here I have an instrument built around a simple vibrating string as its sound source. And it uses all the pitch-changing mechanisms that we've been talking about. I can tune it by adjusting the tension. And notice that the bass string is a thicker string than the treble string. And of course, I can also change the length of the strings and play tunes. Well, okay, it's not terribly successful as a musical instrument. Basically, it's just not loud enough. We somehow need to amplify the sound. You see, the problem is that the string, when it vibrates, just doesn't move very much air. And that means that we don't get enough of a pressure disturbance to our ear. And we actually have exactly the same problem with the tuning fork. Strike it on my knee, you can't hear very much. But as soon as I put it down on this board, I think you'll agree that the sound is now much louder. You see, what's happening is that as the prongs of the tuning fork move from side to side, they force the stem to move up and down. And when it's on the board, that forces the board to move slightly up and down. So now I'm moving a great deal more air, and that produces a bigger pressure disturbance at our ears, so it's louder. So perhaps I should use this trick on the violin. Perhaps what I should do is put the string over a bridge, so that as the string vibrates, it forces the bridge to vibrate, and the feet of the bridge force the chipboard sounding board to vibrate, which means that I'm going to move more air. Now, this doesn't look as aesthetically pleasing as a Stradivari, but see what it sounds like. Well, it's certainly better, but I think you'll agree it's still not as good as we'd really like. Just have a look at this. Tuning fork on chipboard. And now, another board. Let me strike the tuning fork again. Wouldn't you say that was much louder? So, what have I actually done to this second board in order to make it sound much louder. After all, it's got the same area as the chipboard, it's moving the same amount of air, so what's different? Well, that's where a bit of modern technology can help.
At Celestion in Ipswich, they have a system for analysing loudspeaker vibrations. A laser beam scans across the vibrating cone, and by analysing the frequency of the reflected light, which is shifted because of the Doppler effect, the vibration pattern can be processed and displayed on an oscilloscope screen. Unlike a loudspeaker, our board doesn't vibrate on its own, so a driving loudspeaker is used. When the board is placed on top, it can be forced to vibrate at the frequency of the driving loudspeaker. Well, we brought the playback system into the studio so that we can have a close look at the vibrations of our board. What is it we're seeing here? Well, the motion of these lines on the screen represents the vibrations of our board. What we did was to scan across this central section of the board with the laser, and it's the vibrations of this central section that we're seeing on the oscilloscope screen. We're seeing a sort of perspective view of the board. The edges of the board are going up and down in step, and the centre of the board is moving exactly out of step. And in between there are positions where the board doesn't seem to be moving at all. The dominant vibration of the board is a sort of flexing motion, something like this. The vibrations have obviously been slowed down, and the amplitudes have been exaggerated. The edges of the board really only move a fraction of a millimetre. Well, this is what happened when we drove the board just below the frequency of Keith's tuning fork. Let's see what happens when we increase the frequency. Well, it's a similar vibration pattern, but the amplitude is obviously larger. Keep on increasing the frequency, the vibrations are even stronger. So what do you think will happen if the frequency is increased once again? Now the amplitude falls. Keep on increasing the frequency, and the amplitude is now back where we started. So the amplitude increases as the frequency increases. It reaches a maximum, and then it falls off again. And this phenomena is known as resonance. The frequency at which the board vibrates most strongly is known as the resonant frequency. And it's because the frequency of Keith's tuning fork matched this resonant frequency that the board amplified the sound so well. But what is it that determines the frequency at which this resonance occurs? I can give you a clue by showing some more familiar vibrating objects. Well, here are some more forced vibrations. The heavy pendulum is pulling the string from side to side as it's swinging, and that's coupled to the tops of these other pendulums. So they're being forced to vibrate too, or at least this central pendulum is. But why do you think it is that this center pendulum picks up the largest amplitude? Well, remember, the natural frequency of a pendulum depends on its length, and it's independent of its mass. So the central pendulum has the same length approximately as the driving pendulum. That means their natural frequencies are the same. So this pendulum is being forced to vibrate at its natural frequency. For all of the other pendulums, the driving frequency doesn't match the natural frequency, so the response is much smaller. And for the outermost pendulums, where there's a big mismatch between forcing frequency and the natural frequency, there's hardly any motion at all. So resonance occurs when a system is driven at its natural frequency, and the amplitude falls off as the driving frequency differs more and more from the natural frequency.
So the reason why this board sounded louder was simply that its resonant frequency matched the frequency of the tuning fork. But as you've just seen from the laser demonstration, once away from that resonant frequency, and the response fell off dramatically. So the question is, can we widen that response curve? In fact, what is it that determines the width of the response? Well, let me do a couple of experiments with a couple of resonance systems that I know are different. For my first resonance system, I'm going to use these two tuning forks. And I'm going to use one tuning fork as the resonator, this one, and the other tuning fork as the driver. And what I'm going to do is strike this tuning fork. And you can hear that the second tuning fork is ringing away merrily. It's picked up the sound. Now, let me deaden it. I can actually mistune the driving tuning fork by moving this weight up its prong. Now, it won't mistune it very much. It'll be a little bit flatter, a bit lower in frequency. I think you'll agree that now this tuning fork is hardly picking up any sound at all. And the difference in frequency is less than a semitone. Let me just convince you by going back to the resonant frequency again. Ringing away beautifully. Okay, my second system is going to be the air in this milk bottle. And I'm going to drive that with these tuning forks. Let me start off with this one. Well, certainly an increase in the sound. I've got another tuning fork which is higher in frequency. Louder still. The difference between those two tuning forks was a semitone. That's already more than I had on the two tuning fork systems before. Okay, really loud now. That's probably near the resonant frequency. Up again. Perhaps a bit quieter. Another semitone. Still ringing. Another. And another. And another. Okay, it's still ringing all the time, and now I've covered, 5 or 6 semitones above the resonant frequency. That's 5 or 6 times more than I had with the tuning fork system over here. So, what is the difference between these two systems? Look what happens when I just excite this and allow it to vibrate freely. It rings on and on and on. Whereas with the milk bottle, I can excite it by blowing across the top. And the sound dies away almost as soon as I stop blowing. So, hypothesis. A very fast decay time goes with a broad resonance curve. A very long decay time goes with a narrow resonance curve.
The evidence for a link between decay time and the width of the resonance may seem rather circumstantial, since Keith was using two quite different systems. But we can investigate the relation in a more controlled way using pendulums. Look what happens when I set these swinging. The lengths of the two pendulums are about the same, so their frequencies are very similar. But air resistance on the cone is much larger, and so its amplitude decays quite quickly. It's much more heavily damped. Well, we've already looked at the resonance of a set of balls like this. Let's now look at the resonance of a set of more heavily damped cones. The driving pendulum has been swinging long enough for everything to settle down, so let's compare the motion of these damped pendulums with what you saw earlier with the balls. We've made the driver for the damped pendulums, that's the red ball on the left at the bottom, swing further, because it has to supply more energy to make up for the frictional losses. The central pendulums, which are being driven at their natural frequencies, have the largest amplitudes in each case. But I think you'll agree that the resonance curve for the highly damped cones is broader than the curve for the balls. The outer cones are moving more than the corresponding balls. So increasing the damping leads to a broader resonance.
So you might think that all we have to do to broaden the resonance so that it covers the 3 or 4 octaves necessary to amplify the whole range of the violin is go for a dead soundboard. And that's certainly true. That's exactly what we did on the chipboard violin. Chipboard is pretty dead, pretty well damped. But you saw the result. Virtually no amplification. We seem to be going around in circles. Where on earth do we go from here?
Well, as far as amplification goes, the most promising system we've looked at is the resonant board. You've seen that it resonates at one particular frequency, and so it provides good amplification there. But the problem is that the amplification drops off as the frequency increases. But as well as the flexing mode of vibration of the board, this one, there are all kinds of other ways that the board can vibrate. And if we drive it at higher frequencies, we can excite these different vibrations. In fact, there's a whole series of natural modes of vibration for the board, each with its own characteristic natural frequency. And when the board is forced to vibrate, its response curve is the combination of a whole series of resonance curves centered on the natural frequencies. But there are still gaps, frequencies at which the board doesn't amplify. So a simple rectangular plate wouldn't be ideal for a violin.
But a violin has a much more complicated shape, and you would therefore expect it to be able to vibrate in very many more, much more complicated ways, as you can perhaps see from these laser scan pictures. In other words, there will be many more modes in the violin plate's response, particularly at the high frequencies. But that's not all, because a real violin has not one plate but two. The top plate, the belly, and of course the back plate. And normally, as I can show you if I take it apart, these two plates are connected together by a little pillar called the sound post, which sits here, connecting the back to the top. So what happens when it's all assembled is that as the string vibrates, it makes the bridge vibrate, which in turn makes the belly vibrate, which via the sound post makes the back vibrate. So we have two systems now, both of which have their own complex set of modes. And of course, when we glue the whole thing together to form the final violin, we have yet a third resonance system, namely the air in the box itself. And that also has its own complex set of modes. So the response curve of the final violin looks very, very complicated, with resonant curves apparently everywhere. But even so, it does the job we ask of it. It will amplify the sound over the whole range of the violin. And what's more, it doesn't sound too bad musically either. But don't go away with the idea that this is a blueprint for the ideal violin. It's not. It's not the position of the exact resonant curves that matters. It's the interrelationship between them, and also the way in which the belly, the back, and the box all relate to each other. And that's actually the difficult bit, because as yet we don't fully understand the physics of how all these systems couple together. However, things are looking sufficiently promising for us to be able to hope that in the not too distant future, the physicist and the skilled violin maker may be able to cooperate in order to produce violins of the very highest quality consistently.